Okay, let's talk about solution stoichiometry. So solution stoichiometry is just stoichiometry with solutions. Okay, so just like what it sounds like. So let's review. Stoichiometry always involves using a balanced chemical equation to convert between amounts of substances. Okay, and step one of stoichiometry is always to find the number of moles. Okay, so whatever you're given, you're going to convert it to moles. Now, sometimes you're given the number of moles of something, and if so, great, you move on. If not, you need to find a way to find the number of moles. Now, most of the time, that involved taking the given mass, dividing it by the molar mass to get moles. Okay, but when you're dealing with reactions in aqueous solution, um, we don't weigh masses, okay? Because if we did, we wouldn't be able to figure out the moles of solute because there's not a molar mass of the solution. You can't just add water's molar mass in the solutes, okay? And even if you could, how would you still be able to figure out solute? Because it's mixed with some portion of water, okay? And so we have to quantify moles in a different way, okay? And so for a solution, we would know the concentration, okay? And concentration can be in lots of units, but when we're working with solutions, especially solution reactions, we would use molarity, okay? And so molarity, you have to remember, is moles of solute per liter of solution. Okay, so if you have the molarity of a solution, then that means all you need to know is how much of that solution you have. Okay, so how many liters of it you have. So if you know the number of liters and you know the molarity, you can multiply those together and that'll give you the number of moles. Okay, once you have those moles, then you're going to use the balanced chemical equation to convert those moles to moles of whatever substance you're looking for. Just be careful and make sure if you're trying to calculate a theoretical yield of product, then you need to consider the limiting reactant. So if you're actually given information about multiple solutions, you need to figure out which one actually limits the reaction. Most of the time, we have one substance we know about and the other one we're just told it's in excess, or you have to assume it's in excess, okay? But if you do know information about multiple reactants, make sure that you're going through the limiting reactant procedure, which usually is easiest if you just calculate product from both, and whichever one's less is how much you get. Now, a couple other things when you're dealing with aqueous reactions, the balanced equations could be in the ionic form. So I know sometimes that confuses people, but if it's in the ionic form, then you need to figure out where those ions come from. It comes from the things that are in solution. So if you have a solution that contains sodium phosphate, they may tell you the concentration of sodium phosphate, but maybe in the reaction you're given only phosphate ions there. Okay, and that's because when you put sodium phosphate in solution, it splits up into sodium ions and phosphate ions. Okay, and so if you knew the concentration of that sodium phosphate, you should be able to determine what's the concentration of each of those ions just based on what it breaks up into. So if you have sodium phosphate, so if I were to write that down, sodium phosphate's Na3PO4, okay? So really in solution, that's 3 Na pluses and 1 PO4 3 minus, okay? And so if you had, say, a 1 molar solution of that, you really in solution have 3 molar of Na plus and 1 molar of PO4 3 minus, because you get 3 sodium ions and 1 phosphate ion. And so if you're dealing with a balanced chemical equation and it only has one of those ions in there, it's because the other one's a spectator, and so they've ignored it. So you'll have to be able to relate that combined substance to the individual ions, okay? And so I know sometimes that confuses people, but that's why you've got to be really good with electrolytes and how these ionic compounds break down and, looking at ionic equations or being able to write an ionic equation and then utilize it. So as I was saying, you might need to be able to quantify the ion amounts. That way you can relate it to the balanced equation you're given. But most often we'll look at things in a molecular equations, and that makes things the easiest, at least to get started. Okay, so we're just going to do examples because there's nothing more to it. It's stoichiometry. So it's find moles, use your balanced equation, and put things in the units asked for. Done. Okay, that's always the process. Okay, so now this question says what mass of lead-2 iodide is produced from the reaction of 175 mils of 2.25 molar Ki with excess lead-2 nitrate. Okay, so there's a lot going on there, okay? And there's a reaction, and it's not given. So we need to write that down, okay? And so we're told lead-2 iodide is produced from the reaction of Ki and lead-2 nitrate. So first, let's start with the reactants. Ki is one of our reactants, okay? And it's a solution, so it's aqueous. And we have also lead-2 nitrate, so PbNO3, 2, and that's a solution as well, okay? Because these are all aqueous reactions, so unless if it's an insoluble substance, it's aqueous, okay? And those are both soluble. And then we figure our products by, well, one of the products is given, PbI2, right? Lead-2 iodide. But where that came from is, remember, this is a double replacement reaction. We have two ionic compounds reacting. And so if you focus on your ions, you have K plus and I minus, and then Pb2 plus and NO3 minus. And so we swap partners. Okay. And so the PbI2 came from the Pb2 plus and the I minus combining. So our other product is actually KNO3. And you need that because you can't balance the reaction without everything in there. And so now to balance the reaction, we're going to need two of these KNO3s, meaning you need two KIs. Okay. Okay, so that's our balanced reaction, and then it might be helpful to just list what we know. We have 175 mils of 2.25 molar Ki, so 175 mils of 2.25 molar Ki, okay? And then we want to know if we have excess of that lead-2 nitrate, how much or what mass of lead-2 iodide is formed, okay? And I guess I didn't put the phases on the rest of this. The lead-2 iodide is insoluble, so it's a solid, and the potassium nitrate is soluble, so it's aqueous. Okay, but basically we want to know about our lead-2 iodide. So we need to be able to get moles of something else in that reaction, which we can. We can take that volume and molarity and we can get moles from that. And so once we get moles of the Ki, then we can get moles of PbI2, and then we can get the mass. Okay, so that's kind of the steps that we're going to be going through. Now remember, a molarity is moles per liter, so that is the same thing as 2.25 moles of Ki per 1 liter of our Ki solution, okay? So you can rewrite that and it can help you realize that that's basically a unit conversion, okay? And so then also it would be helpful to then, write the 175 milliliters or convert it to liters. And so there's 1,000 milliliters in 1 liter. So it's 0.175 liters, okay? So that's just taking this information and I just put them in more usable forms. This is all the same info, okay? It's nothing new. Okay, so now let's do our actual calculation. And so what I'm going to take is I'm going to start with that volume because the molarity is really a conversion factor. So I'm going to start with my 0.175 liters. You can start with concentration, but I just like to start with the volume. And then I want to get rid of liters and go to moles of Ki. Okay, and so I use the molarity, the 2.25. Oops, go, per 1 liter. So the liters cancels. And now I have moles of Ki, so I can go from moles of Ki to moles of the substance I want information about, which is PbI2. And I look at the reaction, and there's a 2 in front of Ki, so it's 2 moles, and there's not anything in front of the PbI2, so it's a 1. Okay, so that's going to cancel my moles of Ki. And now, what do we want? The mass of lead-2 iodide. So I want to get rid of moles of PbI2, and I want to go to grams of PbI2. And so I need to add up the molar mass from the periodic table. And so lead is 207.2, and then I add that to 2 times iodine, which is 126.90. So that gives me a molar mass of 461.0 grams per mole. Okay, so that's going to cancel my moles of lead-2 iodide. Okay, so now I have 0.175 times 2.25 divided by 2 and times 461.0, and that gives me a mass of 90.8 grams of PbI2 that gets produced from this reaction. Okay. So the difference from the stoichiometry we were doing before is just that we are using a volume and a concentration instead of a mass and a molar mass to get to moles. Okay, so you have to use what information is given to you. So if you have masses, molar mass is going to help you get to moles. But if you have a volume, then a concentration is going to help you get to moles. Okay. Okay, let's do a couple more examples. What's the molarity of iron 3 nitrate if 350 milliliters reacts with excess sodium sulfide to produce 37.4 grams of iron 3 sulfide? So again, there's a lot of stuff going on here. First off, there's a reaction going on and no reaction given. So let's write the reaction. So we have iron 3 nitrate, so FeNO3, 3, and that's going to be aqueous, plus we've got sodium sulfide, that's what it's reacting with, so Na2S, and that's also aqueous. And then it's going to produce for sure Fe, let's see, it's iron 3 sulfide, so Fe2S3, okay, because that we know it produces based on the wording of the question. But the other one we need to figure out by looking at our ions. We have Fe3 plus, NO3 minus, Na plus, and S2 minus, right? And so the Fe3 plus and the S2 minus combine to give us the Fe2S3. And so now we need to combine the Na plus and the NO3 minus. So our other product is sodium nitrate. Okay, and again, I can put my phases in here. Iron 3 sulfide is insoluble. Okay, so we've got our reaction. We need to balance it. Okay, so we're going to need 2 of the Fe NO3 because of the iron 3 sulfide that's produced. And then that gives us a total of 6 nitrates. So I'm going to put a 6 in front of the sodium nitrate. And then I'm going to need 3 of the sodium sulfides. Okay. And so that should be balanced now. Okay, we have our balanced reaction. Let's just write down what we know. Our iron 3 nitrate, we have 350 milliliters. Okay, and it's reacting with excess sodium sulfide, and it produces 37.4 grams of iron 3 sulfide. And what we're asked for is the molarity of that iron 3 nitrate. So molarity, this is what we're looking for. Okay, if we want the molarity of something, we need to know the number of moles and the liters. Now we're given milliliters, so we can convert that to liters. But we need, well, and I guess I can do that real quick. The 350 milliliters, we take that, oops, I lost it. So I'll write it down here. I'm going to erase it. I'm kind of assuming you already know how to do this conversion, but I'll write it down. There's 1,000 milliliters per 1 liter. And so that comes out as 0.3500 liters. Okay, so I'll just write that down. That's going to be more useful to us when we do our calculation. Okay, because we need liters in order to get a molarity. And so that means we also need moles. So if we need moles of that substance, we've got to be able to get moles of something else. Okay, and the other substance we know info about is that iron 3 sulfide. And we have grams. Those grams we can convert to moles. Okay, so we can get moles of Fe2S3 from grams. And then we can use the balanced equation and get moles of NO3. Okay, and then once we get that, then we can get the molarity. Okay, so those are the steps we're going to take. So we're going to start with the 37.4 grams of Fe2S3. Okay, and so then we can convert those grams of Fe2S3 to moles. Fe2S3, and that I get by adding up 2 of iron, so 55.85, plus 3 times sulfur, so 32.07, and that totals to 207.91 grams per mole. So that's going to give us moles of Fe2S3. And now those moles I can convert from Fe2S3 to moles of what I'm looking for information about, which is the FeNO3. And that I get from the balanced equation. So, oops, I lost a number there. There we go. We have a 2 with the FeNO3, 3, and a 1 with the Fe2S3. Okay, and then let's see. That's going to give us moles, which we'll go ahead and calculate that, because then we need to calculate molarity by taking moles divided by liters. So 37.4 divided by 207.91 times 2, and that gives me 0.3598 moles. So I'm keeping extra sig fig there since I'm not done. Okay, so now I'd take the 0.3598 moles and divide it by the 0.3500 liters. Okay. And that gives me 1.03 molar FeNO3. My answer. Okay, so you can be solving for all kinds of stuff. So the stoichiometry part, we just needed moles from that and then calculate a molarity from it. Okay. And so we went from gram information to now information about solution. Whereas the last one, we went from concentration and volume information to grams of something. Okay. You could also be dealing with all solutions and just converting some solution molarity and volume info to some other solution molarity volume info. Okay. So let's do one more. Okay, in this one, we're going to deal with just solution information, so not masses. So this one, I say what volume of 1.5 molar lead 2 nitrate is required to react completely with 50 milliliters of 1.5 molar Ki, which I think we already did this reaction, but I need to rewrite that reaction so that we have it for our stoichiometry. And so you should be able to predict this reaction. You know the two reactants, and it's just two ionic compounds, so it's going to be a double replacement reaction. And so what you end up getting is PbI2 and KNO3. Okay, so this is the same reaction we had before, so you end up needing two of those and two of those. And then we have 1.5 molar of the lead 2 nitrate. Okay, and we want to know what, oops, no, we want to know what volume of that is needed to react with 50 milliliters of 1.5, oops, 1.5 molar of the Ki. Okay. So since this is a reaction, it's still a stoichiometry problem. You need to get moles and convert to moles of the other thing. So out of these two things that we know info about from the Ki, we can get moles. So we'll get moles here of Ki, and then we'll convert those moles of Ki to moles of PbNO3 and then we can get our volume, okay? Because if we have a molarity and a number of moles, then we could get a volume. Now I want to caution you because a lot of times people see this and they see, okay, I'm looking for a volume and this is a concentration and I have a volume and I have a concentration. And so if you're writing this stuff down and you kind of label it this way, sometimes people think, oh, I have two concentrations, two volumes, so I'm going to use C1V1 equals C2V2. Okay, and I'm going to tell you, you absolutely cannot do that. Occasionally you get very lucky and it works. Don't count on it because that is the dilution equation. That is not a stoichiometry equation. So this you should not be using, okay? It will work for a few reactions, but don't count on it, okay? That is not the proper way to do it. For this one, it will definitely give you the wrong answer, okay? So we need to do the actual stoichiometry. Calculate moles, do your mole to mole ratio, and then convert to the units you want or calculate what you want from it. So I'm going to start with my concentration and volume of Ki and get moles. And it would be helpful if you rewrite this as 1.5 moles of Ki per 1 liter. Okay, so that's really a conversion factor. So I'm going to start with my 50 milliliters of that Ki. And I'm going to convert it to liters because the conversion factor I have is in liters. There's 1,000 milliliters and 1 liter. Okay. And then I can get rid of liters and go to moles of Ki by using that molarity. So it's 1.5 moles per 1 liter. Okay. And that gets rid of my liters. and gives me moles of Ki. And now I can take my moles of Ki and convert to moles of PbNO3 So I look at my reaction. There's a 2 with the Ki, a 1 for the PbNO3 And so that's going to cancel the moles of Ki. And so let's see. Now with that, I can stop and calculate it, then calculate volume. Or again, if you realize here we have 1.5 molar. So again, that is 1.5 moles per 1 liter, but that's PbNO3 okay, instead of Ki. But I can use that as a conversion factor. So I could put moles of PbNO3 on the bottom and liters on top, and that's 1.5 moles per 1 liter. Okay, and that is going to tell me how many liters of that solution I need. Okay, so I would take 50 divided by 1,000 times 1.5 divided by 2 and then divided by 1. And so that gives me 0.025, and that's liters, okay? So I need 0.025 liters, which is the same thing as 25 milliliters. If you wanted to convert it, that's fine as well. But I didn't say specifically what volume unit, so liters is perfectly fine there. Okay, so that's solution stoichiometry. It's the same thing, it's just you're dealing with things in different units. You still have to go to moles and use the balanced chemical equation to convert from moles of one thing to another. Okay, again, it can be tempting sometimes with these problems to use the dilution equation, the C1V1 equals C2V2, but don't do it because most often it will give you the wrong answer. Okay.